Okay. Yeah, so I'm going to be talking about a study of guts. Let me start with a disclaimer, and that is, I realize my accent is sometimes a bit annoying and I speak quickly when I get excited.
And you can take off your mask if you're comfortable.
Yeah.
Sure, if you're drinking or eating, which he is if you water.
Yeah. So I'm not going to get into trouble. Yeah, so my accent is, sometimes I say things and it all becomes muddled, and so if there's something I say and you don't understand it, just tell me. I'm happy, it happens all the time. The second thing is I'm dyslexic, and there are going to be names in this talk that I'm not going to be able to pronounce. So if that's the case, I'll try my best, but there'll be names of people you may know and I'm just going to pronounce them wrong. And the last thing is, when I give talks, I kind of like to do it in a different way to most people. I try and experiment with different ways to give a good talk. So if there are things in this talk which you don't think worked, or things that you liked, it's helpful if you let me know at the end, so next time I give it, I can make it better. Okay, so with this in mind, I'm going to split this talk into two parts. There's some research which says the best length for a talk is about 20 minutes long. So I'm going to split this talk into two halves, each of which is going to be about 20 minutes long. And then in the middle, I'm going to do something called a brain break. And it's basically a time, like a minute, where we won't talk about physics and we'll talk about something else, which is exciting. The first half is going to be on the guts of Sp6. And this is with a paper, based on a paper I did with Ben Almack and Ben Koppers, both of whom are at the University of Cambridge. Before I start, I'm going to say I'm using guts very loosely here. I'll explain exactly what I mean as I go on, but I don't mean guts in the, I'm using it very broadly. And in the second half of the talk, we're going to pick an example of a gut, which is going to be Sp4 plus Sp6 plus Sp6, and we're going to discuss it in detail. And this is based on this paper I did with Jody Figi, who is a postdoc in Zurich. And I'm going to try and focus on the broader picture rather than getting stuck in the nitty-gritty details. Okay, so let me flash up some code. I don't want you to read code, I just want you to acknowledge its existence. This code is about 3,000 lines long, and it is the product of the first half of this talk. And it's what this code is and what this code produces, which the first half of this talk is going to be about. And I'm going to tell you the story of how this code came about and what it does. Let me just quickly summarize what it does. It outputs a list of guts, or a list of list of the algebras which the standard model fits into, where you don't have to add any fermions. But I'll get into the details later. Okay, so the story of how this code happened started in this building here. This is the Cavendish Laboratory, and as you can tell, it's basically a block of concrete with holes in for windows. Not only is it ugly, it's also deadly. It's full of asbestos. So it wasn't the nicest place to do a PhD, but it was the people there were nice. Just the surroundings weren't the prettiest. And every Wednesday morning in this building, we used to have a meeting, and it used to be called the SUSY Working Group. And in this meeting, we would talk to each other about the things that we were working on that week. They ended up changing the name from the SUSY Working Group to the FINA Working Group, because no one was actually talking about SUSY, and they didn't think putting the SUSY Working Group on papers was the best publicity for what we were actually doing. So there was this particular Wednesday morning in 2018 when I had just started my PhD, and there were three people in this meeting of interest. There was Ben Almack, Joe Fee, and Scott Malfield, and they were there discussing a question that they were working on. And the question they were trying to answer, or the question they were looking at, was this one. With the standard model plus three right-hand neutrinos, what are the anomaly-free sets of charges under a U1 extension? A U1 extension of the standard model gauge group, or the standard model gauge algebra. So let's break down this question, what they were doing. They took this, so this is the standard model gauge group, the SU3 plus SU2 plus U1. And these are the standard model fermions. And I've added this column here, which corresponds to 3 right-handed neutrinos. And for this first half of the talk, I don't want you to consider the scalars. We're going to put the scalars to one side. We're only going to focus on the fermions. So this is basically the fermionic content of the standard model. And what Ben, Joe, and Scott were doing, or what they were talking about in this meeting, was what happens when you increase the gauge group with an extra U1. And when you do that, all of your particles gain an extra charge, an extra integer charge, corresponding to that charge under that extra U1.
The rows are the different flavors?
The rows, yeah, so this
generation?
is like one family, this is another family, this is your left-handed quarks. I have done something slightly unconventional. I've normalized my hypercharge to be integers.
Yeah. I was freaked out it's -4.
Yeah, sorry. There's a reason I've done this, which is good. Okay, because we have a U1 here, and U1, we're going to assume compactness. And that basically means that when I've added these extra charges on, that compactness condition basically means that these charges have to be integer charges. Okay, so these numbers here have to be integers. And what, so Ben's,
That's an assumption.
that is the assumption that this corresponds to a U1 rather than an R. Yeah. That these label representations of a U1 rather than representations of a R field, which they have the same algebra, but they have different representations. Okay. So what Ben, Scott, and Joe were doing, and what they were discussing in this meeting, is what happened, under what conditions are these charges anomaly free? And this corresponds to this set of equations. So what anomaly freeness means is that you don't run into any problems when you try and take this classical theory and you try and gauge it. They correspond to those triangle diagrams you sometimes see. But for a U1 extension of the standard model, it basically corresponds to your charges satisfying these equations. Okay, so these equations are polynomial, they're all polynomial equations in integers. So these charges, these charges have to be integers. And polynomial equations in the integers are called Diophantine equations. And Diophantine was this Greek mathematician. It's probably one of the less well-known of the Greek philosophers. And it was in Diophantine's Arithmetica that Fermat wrote his local theorem, his last theorem. So you know he wrote his last theorem in the margin of this book. It was Diophantine's book that he wrote that in. And Diophantine was kind of like the founder of that theorem. So Ben, Scott, and Joe, they were looking at this equation and they were talking about how they were going to solve it. And they did perhaps what we would all do when faced with a problem like this. They solved these equations numerically. So ACC squared just corresponds to those equations. So they found a numerical solution. They took their charges and they said, we're going to assume no charge can be larger than, say, 10, and we're just going to scan through it. And we're going to try and find all the solutions given this condition that none of the charges are 10. And they published this paper, which is this one here, and that paper contains basically a list of all of these U1 charges that you can add to the standard model up to some maximum charge. So I was listening to this in 2018. I was listening to this conversation that Ben, Scott, and Joe were having about these equations. And as 2018 turned into 2019, another paper came out. And this was by Costa, Dabrowski, and Fox. I'm going to pronounce that, probably mispronounced pronunciation of their names. But they were looking at a slightly different problem. They were looking at the anomaly equations, which are these, for a U1 gauge theory. It's not a U1 extension of the standard model, but a U1 gauge theory in isolation. So these xi's, you basically have n fermions, say, and each which gains a charge, xi. And for that theory to be anomaly free, they have to satisfy these equations here. And they amazingly found an analytic solution to these equations, which in number theory is something which is quite difficult to do. Solving equations in solving integer equations is difficult, as Fermion tells us. So they managed to find the third general solution to these equations. At the same time as this paper came out, I was speaking to Ben Alanak and Ben Papias, who's my PhD supervisor, and we were talking about projects that I could do which were more towards the pheno side. At the time, most of the projects I had done had been quantum mechanics related, like principal bundles, more like formal stuff. And the suggestion was that we try and solve these equations of standard model plus U1. We try and solve them analytically. So this is what we did. This is what we did in the end of 2019. We produced an analytic solution of these anomaly equations.
Sorry, can you say again how it's different from the Fermion Masses?
This one. Okay. So this is, they are solving these equations, which correspond to just the U1 gauge theory by itself.
Okay.
So not coupled to the standard model. What we're solving, so they're solving these Cavendish equations, these polynomial equations. What we're doing is solving these polynomial equations, which correspond to a U1 extension of the standard model.
Yours would apply to like a hidden sector
Yeah,
where
exactly.
standard model singlet.
Yeah, exactly. So theirs applies to assuming every class doesn't carry a charge under that, whereas ours corresponds to assuming all of your fermions do carry a charge under the section you want.
Just a question about this. So you rescale the hypercharges to be integers from their like conventional fraction, rational numbers. So, but the same could be true for the new U1, right?
Sure.
It's
Yeah.
not necessarily. Is it scaling variant? You're
Yeah, exactly. Good. These equations, they are homogeneous, so you can take any solution of these, any multiple of that solution is also a solution. And that multiple is non-physical. So when you come to solve it, you do something technical, which I don't really want to get into, but you solve it in something called projective space. And that is basically the space of solutions quotiented out by this multiple. So you work in the correct space so that this multiple doesn't matter. Okay. So this is the situation at the end of 2019, and what we have is a parameterization of these solutions. So you can give me a set of parameters, and I can output a solution to these anomaly equations. And every solution to these anomaly equations, every possible U1 extension of the standard model can be classified as the solution to this, or can be found by some parameters in this model. So as 2019 turned into 2020, of course, the COVID pandemic happened, and I moved from Cambridge back up to York, where my parents lived, and I had this conversation with two parents about what can we do next. I wanted a project which I can just work on, that take my mind off the world, and I can just do in my free time. So to tell you what that project was, I need to give you a 2-minute lecture on Lie algebras. Now, this is not going to be detailed, but I need you to understand a few basic concepts. I'm not going to give you formal definitions. I just need you to understand the simple stuff. So I'm going to define a simple Lie algebra. And this basically constitutes all of the Lie algebras that you are familiar with. Things like, or that you are generally familiar with. So things like SON, SUN, and SPN. SPN you may be less familiar with. I'll end up defining that in the second half of this talk. But things like SUN and SON, them themselves are simple. Then we have semi-simple algebras. And these are just product or direct sums of simple algebras. So the SU3 plus SU2 of the standard model, that component is semi-simple. And the SU4 plus SU2 of Pati-Salam, that is a semi-simple algebra. So I feel this is probably known to most people. There's also actually a larger collection called reductive Lie algebras. And these consist of semi-simple Lie algebras plus U1 factors. So they consist of things like SU3 plus SU2 plus U1, which is of course the standard model. And that is an example of reductive Lie algebra. And SU4 plus SU3 plus SU2 plus U1, the 4 through 2 1 gut is another example of a reductive Lie algebra. So I just need you to, you don't have to remember these in detail, just remember that these classifications exist. Okay, so as motivation for what we ended up doing, as motivation for the result of this conversation I had with the two bands, let's take a look at this diagram here. So we're going to look at the SO10 gut. Okay? And the SO10 gut basically can be described in its entirety by this diagram. And this diagram commutes. So this is the standard model gauge group, and this is SU48. So the 48 comes from the fact that we have 48 fermions in the standard model if we include 3 right-handed neutrinos. And throughout this talk, I'm going to kind of call the standard model to include 3 right-handed neutrinos. If you don't, if you just want to consider the standard model, the answer becomes a lot more boring. Okay, so we're going to consider this is like the largest SUN group that can act on your fermions. Okay, and then the SO10 gut. Oh, sorry, let me go. This map gamma is the representation of those fermions. So this contains everything about how the gauge algebra, the standard model, acts on your fermions. The information in this gamma is like that 3-2-1 representation of your left-handed quarks, or the 1-3 bar -4 representation of your up-type right-handed quarks. So all of that information is contained in this gamma. Up here you have SO10, and this is our gut. So SO10 is described by 3 copies of this 16 representation. That is basically what the SO10 gut is. Notice that 16 times by 3 is 48. And then we have the map alpha, which just tells us how the standard model embeds into SO10. Okay, so this is really everything you ever want to know about the SO10 gut is somewhere in that diagram.
Sorry, you said this, but the 48 is the largest group with what property? That it contains a stemmer without extra fermions?
Yeah, so there are 48 fermions in the standard model if you include 3 right-handed neutrinos. So the largest group that can act on them is GLN, so the general linear group. That's the largest matrix group that acts on 48 fermions. And then you require your kinetic term to be invariant, and that reduces it down to UN, and then you can make it SUN by requiring it to be anomaly free.
Why SU48 and not SO96? Because after all, I mean, you can just double it, I mean, you run.
So you want to do what? You want to
take left-handed and right-handed and have or if you want, take a Majorana representation, and because we know that you can do
yeah, so this contains the left-handed and the right-handed. Do you want to? I can't see how you.
Well, I mean, instead of vial, which is just a
name,
you right? It's nothing. Use write them as Majorana. Then you have 4 real for each fermion instead of 2 complex. You'll have an SON, but you double the number, the number of fermions.
I can't answer that off the top of my head, but I think the answer is something like it won't work well with the Lorentz group acting on it. You kind of need these things to be separate.
No, this works well. I mean, this is I think that Cyber uses all the time. So,
Okay.
but, I mean, there may be something obvious with the assignment of chirality, etc. But in principle, you could start with SO96.
Yeah. Okay.
Just take the free action if you want.
Yeah.
The free action of fermions. Represent it alla Majorana, right? And you have 96.
Yeah. I guess one could do it. It would be more difficult than doing this.
But you didn't talk about the exceptional algebras, right?
No. The exceptional algebras they are there, but they're not going to be in our solution. So I haven't mentioned them, basically. Yeah, they exist, but they're not in our solution. So which is why I haven't made a big deal about them. Okay, so we're going to take this diagram and we're going to generalize it. So this is like this diagram, but I generalized it. So I put a generic beta, a generic G, so it's generically algebra, and then a generic embedding alpha into that algebra. And we can ask, can we classify, can we find all diagrams that look like this? The answer to that question is obviously no. There are far too many G's that can be here, far too many different groups that can be there, or gauge algebras that can be there. So you need to start putting conditions on G such that you can classify all of these diagrams. And the holy grail, let's say, of this type of study is to find all G which are reductive. So this would contain things like the flipped SU5 gut or the 4321 model. That's too difficult because of these U1s. These U1s make it really difficult to do. So what we ended up choosing, or what we ended up doing instead, is we want to find all of these diagrams where G is semi-simple and the representation beta is free of local anomalies. So you want it to be anomaly free just because you want to be able to gauge this quantum mechanically. You don't want to run into problems at that level. Okay, so let me just say what we're doing in different words. We want to find every gut that can act on the standard model of fermions without adding extra fermions to the standard model. So we're restricting the number of fermions to 48, and we're going to find all of the guts that can act on it. So whenever you start a project, you need to know that it can be done. There was no point of me and the Bens trying to do this project without knowing that it could be done in the first place. So how do we know that this problem, finding all G, where G is semi-simple, has a solution? This is because of the work of Dinkin and these people whose names I'm not going to be able to pronounce. And they basically, well, Dinkin in particular is famous for classifying semi-simple algebras. He's Dinkin diagrams, and he also has papers on semi-simple subalgebras of semi-simple algebras. So this basically contains all of the ingredients you need to find that diagram. So the mathematics was already there. And what we needed to do is put that mathematics into practice, which is what that code at the very start of this talk did. It basically just tried to find all of those diagrams. I'm not going to go into detail about what the code does and how it works because I don't think that's going to be useful for anyone. What I'm going to do is instead give you the results. So for one family, so this is, take just one row of that list of fermions that we had. There are exactly 3 guts you can have, and they are the ones that you are probably most familiar with. They are SU5, Pati-Salam, and SU10. Notice that I'm calling this a gut. Some people wouldn't, and this is, like I said at the start of this talk, why I'm using a forward slash the word gut. Both SU5 and SO10, both SU5 and Pati-Salam sit into SO10. They embed into it. So really, I'm only going to talk about these maximal ones, the ones that don't embed into anything else in what follows. In the 2-family case, there are slightly more solutions. There are 45. And here are some examples. So there's SO10 plus an SU2 flavor symmetry, which basically mixes your families, your 2 families. There's SU5 plus SU2 plus SU2, which is just a random combination. You've got some family mixing going on there, and then some of your neutrinos get mixed up with this SU2. We have this one, which is a slight variation of Pati-Salam. I'll explain this in more detail later, or a variation on that later, but you get 45 algebras. So what about the 3-family case? In the 3-family case, you get 340 algebras altogether, and 24 of which are maximal, so they don't embed into anything else. And these are the maximal ones. So I won't go through them all in detail, but they are perhaps familiar algebras. This is SO10 cubed, for example. There'll be things like Pati-Salam cubed, which has been popular in the anomaly community recently, and variations thereof. Okay, so this is the end. Remember I said I'm going to split the talk into 2 equal halves. This is the end of the first half. So what are the 3 messages I want you to remember from this first half of the talk?
Sorry, to go back for a second. You have, just trying to understand the notation, when you have these pluses in the exponent,
Yes,
that
I just need 2 copies.
Okay, yeah.
Yeah, sorry, it got a bit too long to write them all out. Yes, this top one is Su4 plus Sp6 plus Sp6, and that is the one we will be looking at in the second half of the talk. Okay, so the 3 takeaway points is progress has been made classifying guts. I really shouldn't put guts there, I should say extensions of the standard model gauge algebra. And there are 340 possibilities of semi-simple guts, as long as you don't want to add extra fermions. And this number is big, but it's not too big. So one can imagine systematically going through them and looking at properties thereof. And importantly, I haven't said anything about scalars. So remember at the start I said, let's just focus on the fermions. There's nothing in this talk, this first half of the talk, that mentions scalars. I haven't said anything about the scalar sector of the model. Okay, so it's time to stop thinking and have what I call a brain break, where I'm going to talk about something which is not related, well, it's kind of related to physics, and it's the conclusion that me and the 2 Bens had about what we call this paper. When you've written a paper, you have to come up with the name of the paper, and what we ended up calling it is this word here. So this is floxy-noisy-nilahilification, and it is the longest non-technical word in the English language, and it basically means something which is or classifying the worthless, and it's basically made up of a bunch of words which mean like a trifle or nothing or something which is worthless. And if you search this on the arXiv, you get 5 papers. This is the paper that we have. This is what we called it. Initially, we just called it this word. I'm not going to say it again because I'm going to mispronounce it. But PRLs legitimately said you can't call a paper that, so we had to, or PRD, we had to
use it in a sentence.
Pardon?
Use the word in a sentence.
No. It's been used in the UK Parliament, so it has been used in the context of, I think it's used by people showing off, but yeah.
It is the longest name that is not a name of a place, right?
Yeah, so
I remember a Welsh village that
Yeah.
definitely longer.
Yeah, exactly. I think there are chemical elements also which are longer, but it's the longest one which is not like contrived or like not. It's contrived, but it's not
enjoyed.
Yeah, exactly. Not technical. The other paper. So this is the paper that I've been talking about. This is a paper which is just like a self-citation. This is one on machine learning. I tried to read it. I couldn't understand it. This is a paper on word length, and now this one is interesting. So if you notice the date of this paper, it was published 2 years ago today, which is just in time for April Fools. So this is an April Fool's paper on quantum Gordon's law. And Gordon's law is basically saying that as a discussion on the internet proceeds in time, it will eventually converge on a given topic, such as philosophy. And what this paper is saying is, when quantum computers come around, it will converge. That convergence will be quicker because of quantum computers. It's not a real paper, but it's fun to read. Okay, so let's go on to the second half of the talk. So this is me slightly seen last night, and lots of people were taking a picture of this building, which is famous for some reason. But what I was taking a picture of is this shop here. So this is Build-A-Bear Workshop. Now, if you've never been into Build-A-Bear Workshop, it's quite, well, I've never actually been in, but I've heard it's quite fun. You basically go in and you build a bear. You pick up the skin off the bear, you find the stuff in, and you make the bear. And what we're going to do is we're going to do something like build a gut workshop. So we're going to choose the outside of our gut and we're going to build it up. Okay, so what's the first thing we need? The first thing we need to build a gut is, I should say, by the way, the second half of the talk is really disconnected from the first half. So if you've lost me in this first half of the talk, you can try and rejoin now. It's kind of disconnected, it's related, but it's hopefully it's independent as well. So I've taken that big list we found in the first half, and I've taken some examples from that list. And I've taken the examples which have the least number of fermion representations. So this one only has one fermion representation, this one has two, and so on. So when you go into build a bear workshop, the first thing you do is you pick the skin of your bear, you pick the outside, and here what we want to do is we want to pick the basis of our gut. We could pick this first one, but this is pretty boring. So this is like an SO10 gut with an SO3 or SU2 family symmetry, which just rotates your three families of your quarks or electrons. So this is not particularly interesting. We could then choose, so ignoring the first one, we could then choose one of these three. And you kind of just have to choose one and roll with it. So what me and Joe DeFigi, who is the person I did the second half of the project with, or this second project with, what we ended up doing was choosing this SU12 plus SU2 plus SU2 gut. So we took that gut and we tried to build it. So we tried to make it as pretty as possible. So like when you go into build a bear workshop, you pick the outside of the bear, you try and make it look as nice as possible. The result we ended up getting wasn't particularly nice, so we ended up throwing it away and ignoring it, like you would throw away an ugly bear, I guess. And so we moved down the list, and we then looked at this SU4 plus Sp6 left plus Sp6 right gut. We could have also looked at this bottom one. There wouldn't be that much difference looking at this bottom one to the one we're going to look at. So if you're particularly fond for any reason of this one, I don't know why you would be, of this one compared to this one, you can basically translate my talk into the bottom one. So I guess a question, oh, I should also add, this studying this gut is not actually a new thing. There are a bunch of papers from about, I think the 80s or 70s that also looked at this gut, but not in the same direction that we did. Okay, so I guess the question that some of you are maybe asking yourself is, what is Sp6? Because you probably know what SUN is or have an intuitive idea of SUN, an intuitive idea of SON, but Sp6 is pretty uncommon. So let me define it. You don't need to know this definition. I just want to show you a definition exists and it's out there. So Sp6 is defined as the subgroup of SU6 such that this condition holds. Okay, so this is the Lie group, and then the Lie algebra is defined like this. So you don't have, there is no relevance of this definition for this talk. I just wanted to show you that they exist. There are other non-equivalent definitions. So some people define it not as a subgroup of SU6. It's this definition that we need for our talk. For this talk.
So you need really USB6, the compact.
Yeah. We ended up calling it Sp6 because if you keep putting the U's in front of everything, we got a bit messy. Okay. So, ignore this slide for a second, just listen to me talk. When you go into build a bear workshop, once you pick the outside of your bear, you need to choose the filling, you need to choose what you want to put inside it. And this is the same with the gut. We kind of have some of that fill-in already because the fermion sector was given for us by the last part of the model. The rest of the fill-in is the scalar sector. So we need to choose the scalar sector of our model. And for us, the scalar sector is going to be completely determined by the symmetry breaking pattern. So we're not going to need any more scalars in our gut than those determined by the symmetry breaking pattern. And the symmetry breaking pattern we want to do is this one here. And I realize this is a fairly full-on slide, so let me just point out the key bits of information. So let's consider this Sp6 left bit. So this contains really all of the left-handed fermions of the standard model. It unifies them, it unifies the flavor, the three families of the standard model into this Sp6 left. We're going to break this down to the Su2 left, or 3 copies of Su2 left. Okay, so 1 copy for each family of the standard model. And we're going to do that with this field S left. Okay, and then we're going to break that Su left, that combination of 3 Su lefts, down to this 1 Su left, which is in the standard model. So this is basically the standard model down here. And we're going to do that with this phi left. Okay, so that's the left-handed sector. The right-handed sector works in a similar way. You have this S right, this phi right, which mixes the groups in a way which is desirable. The details of this are not important. The standard model is then broken, or electroweak symmetry is then broken using 2 Higgses, and this is typical of Pati-Salam type models. So this is related to Pati-Salam, which is of course Su4 plus Su2 plus Su2. Sp6s. So we're going to need 2 Higgses, and this is just to get the Fermion Masses to work. And what we're basically gonna do is work at this level. So we're going to write down an EFT at this intermediate level, where we've integrated out some of the heavy components of the Higgses, and we're going to try and get this to work. So this is kind of the stuffing of the bear. You don't need to remember the details here, just note the existence of the scalar sector. The S left and the S right, they don't really play a role, and you will see the role of these other things in a second.
So is this the only breaking pattern that's giving you the standard model in the end? Or can you break it in one step?
Can you break it in one step?
Or can you break it with a different intermediate group?
You can definitely break it with different intermediate groups. So this is not
unique.
It's not unique. Yeah, so actually, what these papers do, is they basically classify the breakers that you can have.
So, sorry, can I ask a question where we're going? You're going to say that this is a phonologically viable extension?
Yeah.
So you're going to tell us about the scales of the breaking and the scalar components and what they're mediating and all this stuff. That's
So
wait for later.
What I'm going to do is going to tell you the fermion, how we're going to get the fermion masses from this. Okay. So notice there's an epsilon here. So we have this scale lambda h, which is the scale we're going to integrate out the heavy Higgses, and then this breaking happens at the scale epsilon lambda h. And what we're going to do is we're going to take that epsilon and we're going to move it to the fermionic sector, the fermion mass sector, and we're going to predict the scale and the hierarchies in the fermion mass sector. Okay, so yeah.
Can you explain this thing about how 2 Higgses break the
You want to know why we have 2 Higgses, or
like how's that consistent with our picture of the standard model Higgs?
So your standard model Higgs will be a linear component of parts of these Higgses. Yeah. So once you've got down to this point, you have a component of your fields which will add up to give the standard model Higgs.
I see. Okay.
This is the same in like 2x doublet models, or like
It's like the equivalent of h up and h down in Tooby models.
more or less, I guess. Okay, so this is like the feelings of the bear, and now we need to do, as Josh was saying, is we need to work out how to like fix it up. How do we make this into a paper? Where are we going to take this? Okay, and there are a bunch of different things we could now look at. So we could look at Fermion Masses. We could look at neutrino masses. We could ask, does our gut predict low-scale unification? We could study the B anomalies. We could look for C primes in our gut and ask if there are B anomalies. We could look at cosmological consequences, look for cosmic strings, monopoles, things like that. So there are a bunch of different things. I mean, guts are obviously very broad. Once you've got a gut written down, there are lots of things you can do with it. So we need to choose one of those. We need to choose one of the stitches of our bear to make this a complete project, to make this paper. So what we ended up doing was looking at this Fermion Masses. So this is where I'm going to go now. And what we're going to try and do is we're going to try and predict the structure you have in the Fermion Masses in the Ckm Matrix of the standard model. Okay, and this is how we do it. So this slide is very full on. So let me again just point to the important bit. So what I want you to take away from this slide. So we're only going to focus on the down type quarks. So everything I'm going to say holds generically for the up type quarks. So we take a look at this diagram here. So this diagram has color lines in it. It has this blue line and it has this red line. And what the blue line is telling you is something related to that Sp6 right part of our gut. And what the red line is telling you is something about the Sp6 left part of the gut. And 3 arrows basically means this corresponds to the third family. Okay? So this is a third family here and a third family here. So this is going to contribute to our Y33 component of our gut. And what we have up here is a dictionary of the sorts of constructions that we can have. So notice that our Higgs it can take in. This is a consequence of the Fs that we have for these particles. I haven't written down the Fs, but as a consequence of those Fs, this Higgs can take in 3 blue lines, 3 blue arrows, and output 3 red arrows. So we can write down this diagram. Okay. So that is consistent thing to do within our model. I'm not explaining where these come from, just because that would involve me writing down a bunch of long equations and a bunch of guts and a bunch of Fs.
So what is epsilon? Is the power quantum constant?
Epsilon. So epsilons are small quantities. So do you remember on this here, I had this epsilon here. Epsilon is basically, it represents how small the scale is compared to the scale here.
So Higgs, Harry Higgs.
Yeah, exactly. And there are 2 eps. When you write down the Fs, which maybe I should have done, there are 2 epsilons in this, and there are 2 epsilons in that. And
Well, is that a symmetry breaking scale? It's a mass.
it's a symmetry breaking scale. Yeah, so if we take a look at this diagram, and hopefully this will become more apparent, I have 3 lines here. So this is for the 1-3 component and 1 arrow here. So I have 3 arrows here, 1 arrow here. And we look at this up here, and we can see we can take 3 arrows into the Higgs, and then we need to go down to 1 arrow here. So we need to use these phi lefts, which can convert 3 arrows into 1 arrow. And doing so, you get these epsilons. And as I just said, these epsilons are small numbers. So they represent how small these Fs are compared to this integrating up scale, to the scale you're integrating up the Higgs. And you can do the same for this component down here. For the 2-2 component, you can do the same for all of the components. Okay, so I'm just trying to, I guess the purpose of this slide is to give you the basic idea of where these Yukawa couplings come from, where these Yukawa scales come from, without trying to, maybe this is too simplified, but I'm trying not to.
So this, yeah, to summarize, so the 1-3 would be the Yukawa coupling mixing the top and the up quark, for example, or is it in the quark sector? Is it in the left-hand side?
No, yes, this is, I'm doing it for the down quark sector.
Oh, down quark, okay.
Yeah, but to these diagrams for the down quark sector, it holds exactly the same for all of the others.
But that will be different scalar, different Higgses then.
Different components of the Higgs. What basically happens is all these arrows get converted and you get a different component. So the epsilons will be the same, but the order 1 numbers times them will be different. Yeah. Okay, but this is the basic structure of the basic structure you get of your Yukawa matrices, and they all have this structure for the charged electrons, for the up-type Higgses, up-type fermions, and the down-type up-type quarks and the down-type quarks. So yeah. But the order 1 numbers, which I haven't written down, they will all be slightly different, and they will all be functions of the parameters. Okay, so we've made this bear, we've made this gut, and now we need to take it to the playground and we need to compare it with the experimentalist gut, or the experimentalist's bear. Because the experimentalists, they have this perfect bear which your gut and your model has to be compared with. And your experimentalist friend is like, their bear or their gut, they predict this hierarchy in the masses. And they ask us, does our model have this hierarchical mass structure? So what we do is we take this Ckm matrix and we find the masses. And you can show that your first family of masses has 4 epsilons, your second family of masses has 2 epsilons, and your third family has 1 or no epsilons. There are obviously, and this is not for the oneness dimensional factors of B squared there. But we get this hierarchy. These epsilons are small, remember? So this first family is much smaller than the second family, and that's much smaller than the third family. So there's this natural hierarchy that comes in, which is translated from the symmetry break-in into the fermion mass sector by these diagrams, by the scalar potential. So then your experimentalist friend is like my bear or my gut. It not only predicts this hierarchy in masses, but it also predicts this mixing of matrices, or this mixing of quarks in the Ckm matrix. So we need to compare our model to the Ckm matrix. And what we can do is we can do a perturbative analysis on this Y, and we can find its eigenvectors and eigenvalues, and we can find the Ckm matrix. And you get this structure here, where these epsilons are, of course, small numbers, and these C1, C2s, they are order 1 numbers, functions of the scalar potential. And if we take this structure and we compare it, and we take this epsilon lambda 1, 2, which so far I've just said it's a small number, its value can be determined, it's free to choose. We take that to be lambda, and we take this epsilon lambda 2, 3, we take that to be, notice also here there's only epsilon lefts, and that's just the fact that we have a left-right symmetric type model. Sorry, let me go back to what I was saying. We have this epsilon left 2, 3, and we let that be lambda squared. You get this structure here, which has the right hierarchical structure for the Ckm matrix. Okay, but that's not enough, because your experimentalist is like, okay, it's fine that you've got all of this structure and that you've got the hierarchies in the masses, but what about the order 1 numbers? What about the actual values? Can you predict them? In other words, they ask the question, there are order 1 numbers here that I've left undetermined. Is there enough freedom to fit the data? And the answer to this question is kind of. We have enough parameters, we have enough freedom in our scalar potential, which I admit I haven't written down because it's a mess. Well, it's not a mess, but it's just long, and I won't be expecting to remember it. We have enough freedom to fit the Ckm matrix and the top and all of the fermion masses, as long as these conditions are satisfied. So as long as these conditions, so these are basically the components of the Ckm matrix, and this is the Jar-Log invariant. As long as these conditions are satisfied, so these are basically predictions of our gut. Our gut predicts that these relations hold. As long as these hold, then our gut can fit the order 1 numbers.
Can you also predict the CP violating input?
Yes. That's just in the Jar-Log invariant. This Jar-Log invariant contains the CP violating input. So we can ask, does the standard model satisfy those equations? If you plug, or the experimental value, does it satisfy those equations? And the answer is yes, to a pretty good degree, or within 1 sigma. Basically.
Are all these consequences of Wolfenstein?
Yes, they are. Yeah. So these are basically, like Josh would say, these basically follow from the fact that our parameterization matches very closely with Wolfenstein parameterization.
So you would have a similar type of mixing situation for the leptons, right? You would carry this story through for the leptons, but
We have, yes, yes. We haven't looked at it in much detail because we wanted, so there was, we spent ages trying to get the neutrino masses to work.
right, that was going to be my next question. Yeah, 'cause
Yeah.
the mixings and the mass hierarchies are different.
We spent and we got it to work. We have like a model that works, but it's just really ugly. So we didn't end up putting it in the paper because we were like, this is much nicer, this is much cleaner. You don't need anything extra other than the scalars to break the symmetry. And then we went, and then when we had drafts of paper where we had this discussion of the neutrino sector, and it just became long, and it became like we have to add this scalar, so we can do it, but not in a nice way. That makes sense. Okay, so let me give the 3 takeaway points. We have electric flare unification. We had the gut that we were looking at. Maybe I didn't emphasize this enough, I don't think. We have this SU4 plus Sp6 plus Sp6. In this, we have basically unified flavor, the 3 families, with the electric weak sector of Pati-Salam. So this really is like, not only does our model kind of predict the fermion masses, but also, if it's true, would predict the 3 families of, it would give a natural explanation, let's say, for the 3 families of the standard model. It predicts correct structure for Ckm Matrix and Masses, and there are exciting possibilities for future work. Remember that I had that slide with that like semicircle on where it's like Fermion Masses, neutrino masses, all of the other things on that list we haven't done yet, except for neutrino masses, where we kind of looked at. So there's a bunch of different things we are planning on looking at in the future. But yeah, thank you for your attention. If you have any questions or comments.
Well, you remember when I asked about this SU48? Yeah. Actually, you're right. That's the biggest group because all your multiplets were already left.
Yeah,
so
yeah.
Okay. That's still. Are you thinking about the exceptional algebras?
So the exceptional algebras are there. They're in the program, but the results of the program. So there are none there because we're not adding any extra fermions. So there are literally just none in that list where the exceptional algebras come into it, which is why I haven't made a big song and dance about the exceptional algebras. What I am looking at with another postdoc at Cornell is to extend this program. It only goes up to 48. This computer program, it only goes up to 48 fermions. We want to make it more general. We want to basically rewrite it and make it more general to look at supersymmetric guts with like 4 families. I know it's probably not that interesting, but it might be. You might get weird things coming out, just like generic larger guts and with different types of constraints on it. It can be done. It's just the maths is there. It's just writing a program to do it.
Yeah. So if you, from the question about neutrino masses. So if you say, just forget about the singlet that lives in this 48 or the 3 singlets that live in this 48, and you said, well, nature gives me 3 other singlets out there. Can I write down higher dimension operators that can give me the appropriate flavor things that I want for neutrinos then? I mean, do I have a lot more freedom then to do that?
So you were saying take the 3 singlets that come out of 48, just ignore the fact.
Yeah, who cares?
Yeah, they're just random other singlets.
Maybe they've got some Yukawas, but maybe those are not the dominant because those guys end up being really heavy, and there's some other singlets that are lighter. And then you integrate them out, and you just get the Weinberg operator from some other way. Life goes on.
Yeah, maybe.
So are you asking if you can do it like consistent with the gauge symmetry? Or
Yeah, consistent with the gauge symmetry using his fermionology kind of flowing through like.
But they are charged into the 48. It's not.
They're charged into 48, but I'm saying so for sure you got those singlets.
Yeah, they're there because
they're there.
Yeah.
But they can be really heavy, and they probably do. I mean, who knows? I don't know, but they probably do generate some neutrino mass, right? But it doesn't have to be the dominant contribution, right?
So what we did and I ended up doing is our solution to the neutrino mass problem was to basically do a combination of type 1 and type 2 seesaw. So we used those three right-handed neutrinos, but we also had type 2 seesaw, which they didn't. And I think it could have ended up that you could have just done it with type 2 seesaw, where those three right-handed neutrinos, they didn't actually really need to be there. So you can definitely do this. And I think that's the road we were kind of going down, because we had this combination of type 1 and type 2 seesaw. But when we got to this point and we had like this weird combination of the different types of seesaw mechanisms, we were like, okay, let's just stop, write this paper, focus on neutrino masses, let's try and get to like a different type.
Because from a flavor perspective, they just look so different. So, you know, like trying to make them all necessarily. The other question I have is do you predict, from a quantitative unification point of view, like gauge coupling unification point of view, or, you know, whatever you want that to be for like Pati-Salam, do you predict any sort of light matter that you need to worry about that's going to change? It's hard for me to keep track of like whether anything ends up being like excessively light, and I need to keep that.
Yeah, good question. No, because as the model is written down now, this scale lambda h can be incredibly high. You can push that up however high you want, and that doesn't change anything I've told you. It changes.
Might change the running of the gauge.
It might change the running. Yeah, okay. It will change the running of the gauge couplings.
But to Neil's point, like to make the couplings unify at lambda h.
Yeah, sorry.
Or at lambda l. Does it
Unified depending on how they're embedded, and run what couplings you want.
No, but like given an embedding, there's probably like a preferred region for lambda h.
Sure.
Just like there is in SUSY, right? They get
Sure, I'm saying I don't know that they'll all have to be the same here for in what units you want is.
Or at least lambda h's.
What's the relationship between the SU3 and SU2 coupling of the standard model at the scale lambda h? Like an SU5, they're the same.
Yeah, SU5.
Yeah, I don't know what they are here.
I can't imagine there's a reason for them. This is why I disclosed it, saying we're not actually unifying, we're not doing proper guts. We're not really considering, we don't really consider what happens to the gauge couplings. I don't think there's a reason they have to match.
Well, is that, sorry, this SU2Li is where RSU2L lives?
Yeah, so SU2, yeah, so this is like 3 copies of SU2L and 1 ax on each family.
Oh, okay, so those are all this.
Yeah, so it's like this SU2 left is in the diagonal, in the diagonal of these SU2s.
Okay. Yeah, so good. The 3 and the 2 couplings are just unrelated then at the scale lambda h, or they're just free parameters.
Yeah, exactly. So I mean,
and then SU2L lives inside SP6.
Yeah, so SU2, the only thing that's in S from down here to up there, the only thing that's in SP6 left is this SU2 left.
So the 3 and the 2 are just independent. I don't know how the U1 tracks.
The U1 is it's basically the same as what happens in Pati-Salam. The SU3 and part of the U1 is in the SU4, and the other part of the U1 is in the SP6, right? So the U1Y is in both SU4 and SP6, right?
Is that true then, that in Pati-Salam there's no like relation between G3, G2, and G1? I don't know.
It's just a free.
It's a free.
If it's really just 422, then if it's 422 in SO10, then you do.
Yeah. Okay. Yeah. So I mean, this is everything like this that holds in Pati-Salam tends to hold for our model as well. So it's gonna be.
But then you do have a quantitative prediction if you try to embed this in SO10.
We can't embed this. Sorry.
Oh,
you can't
not
embed
this
this.
one,
In
okay,
yeah,
yeah,
you can't
okay.
embed this in SO10. Yeah, because these groups are too big.
How generic is this? Like, have you tried some of the other 300
Yeah,
What
yeah.
did you expect?
Okay. I'm going to be honest with you, most of the gauge groups are pretty boring in this 340 list. There are things like Pati-Salam, SO10 cubed, which is not particularly interesting. There are weird combinations of like one family in SU5, one family in SO10, and then some weird things happen with the neutrinos. So out of the collection of guts that we have, the interesting ones are basically these. Everything else, I should say, and I should have said, in this list of 340 guts, if I gave you enough time, you could probably sit down and think about them and tell me that those guts were there in that list. None of them are like intrinsically new or like intrinsically could not have been thought of about this program. What the program tells you is that there are no more. That is it. So to answer your question, your question was like how generic?
Yeah, like are you able to get the Yukawa?
Good question. I would say
Something special to your choice of algebra?
we couldn't get it to work in this case. So we couldn't get it to work in this case because you can't do this thing where you have two Higgses. Because here you've like unified, I should have said this in the talk, sorry. Here you've unified like flavor with the electroweak, whereas here you've unified flavor with this SU12. Now if you do that, you can't write down, you can't do this to, the reason you have two Higgses is to separate the third family masses. If you only have one Higgs, you get a relationship between, I think it was the top mass and the tau mass. And you can't do this in that example because you end up getting a relationship between the tau mass and the top mass, which just doesn't hold. I should say that it's not like we looked at this model and we just wrote this all down. There was a lot of let's try this way of doing it and it doesn't work. Let's try changing it again and then moves around. So there was a lot of like fixing it to get to work.
I mean, not a zero question, but why did you have to? What happens if you don't add the right-handed neutrino?
Good question. Very good. You mean in the list?
In the list, so you have a less
Very
fermions.
good question. Very good question. You get SU5, SO10. No, you get SU5. SO5 cubed. No, the everything else is boring. It's like, yeah, so in the one family case, you just get SU5. In the two family case, it's just things based on SU5. There, you need the three singlets to get things like Pati-Salam and to get things like SO10. So there are some math, which is why we added it, because otherwise the answer is very boring. And then there is, of course, a question of why add 3? What happens? All of these, like Pati-Salam, SO10, they're known. What happens if you add 4? What happens if you add 5? And yeah, this is the question which I think is interesting. I don't know where the answer could be, you don't get anything more exciting than this. But the answer might also be, you get these new weird things that no one's ever thought of before.
So if you make the scale low enough, like do you have any, like the phi's, the phi L and phi R are light. If they're light enough, then like what would be interesting logically? Are there leptoquarks?
So yes, there are leptoquarks. There's no proton decay for the same reason you don't get proton decay in Pati-Salam. So you can take it, like naively, you can take this lambda to be small. You get leptoquarks, and
So the first thing you'll run into are flavor bounds, I guess.
yeah. So
But the epsilon is kind of determined by your hierarchy in the Ckm matrix.
if you want to be solo.
But lambda h can move around.
Lambda h can move. Your epsilon, so your Ckm matrix is determined by these epsilon, so it determines the relative scale.
Yeah, but I saw your lambda h is more 10 to the 15. Or
No,
It doesn't have to be.
said where it is.
Yeah. So naively,
You're not looking for the 3 and the 2 to unify.
yeah, exactly. So naively, you're absolutely right. Lambda h being like 10 to 50 GP is like where it should be, but there isn't. It's just saying there's no reason at all that lambda h can't be low. We're not stopped by if we have proton decay at like the 3 level, then or like dimension 8 level, the lambda h would have to be high. So we don't have proton decay, but we don't have proton decay at least at like any level that we could see. So this is a project we're looking at. We'll plan on doing at some point. There are elliptic quarks, and there is a this is where my knowledge of like the more pheno side of it breaks down. But there are elliptic quarks there which we think might be able to explain things like the B anomalies. But there are also other things which you get there as well, which we need to track constraints on.
Sure.
So yeah, this is one of the projects we want to do in the future. Just look at the elliptic quarks.
Can I ask a group theory question?
Yeah, that's right.
So if I have one generation and I want to put all the standard model fermions into a single multiplet of a gut, and I have to go to the 16 of SO10, like you were saying, right?
Yes, that is the only thing.
And then I need to add right-hand neutrinos. Yeah, but you're talking about now, combining flavor symmetry and gauge symmetry together. So is there anything, is a 48 the smallest thing? So I can, in my mind, I can be like, okay, well, I did a 16 and then I got 3 16s and then I had my 48.
Yep.
But if I kind of but that kind of in my mind, I'm kind of going, okay, I'm going to the 16 and then I'm putting 3 16s. But if I didn't do that, if I just had 3 10s and 3 5s, could I do something that's less than a 48? Could I do it into a 45? So would there be a way to do that, or would that just not work?
You want to do what? You want to do?
But all I'm saying is that to put one generation into a single multiplet, I have to go to SO10.
One generation, yes.
But if I put all 3 generations into a multiplet,
In a single multiplet.
could I do that without adding the right-hand neutrinos?
Ah, I see.
I'm guessing the answer is no, but I don't know. You might know.
No.
I need, if I want to put everything into a single multiplet.
You can do it with right-handed neutrinos.
With right-hand neutrinos, you've done it, right?
Yeah. This one I showed you without right-handed neutrinos. No. This goes back to the comment, which was the only thing without right-handed neutrinos is SU5. So now you can. Yeah. The thing that I like about this list is that it's really easy for me to answer questions like this because the list is there.
Yeah.
And it's like that is it, which is nice. But no, you can't.
Well, on that note, let's thank Joe again.